All right. Thank you, Cindy. Welcome, everyone. This is our third and last day of the inaugural RRoCCET21 conference. Just our standard information, if you happen to be joining us for the first time, this conference is brought to you by CloudBank, an organization whose mission is to facilitate and accelerate research computing on the cloud. So CloudBank is a collaboration between UC San Diego, the University of Washington, and UC Berkeley, together with Strategic Blue. And CloudBank is sponsored by and originated from the National Science Foundation Computer and Information Science and Engineering Directorate. The purpose of this conference is to inspire you to consider using the cloud in your research. Our presenters are sharing how cloud adoption in their domain enabled them to move their research computing ahead. So we hope that the proceedings which follow, which we are providing for you, will give you an idea of what is possible. It can act as a recipe book for mapping powerful computational resources onto your own field of inquiry. We also hope that you'll take away an appreciation of CloudBank as a cloud access facilitation program. So for more on that, on CloudBank, please visit our website. And that's cloudbank.org. And you can also reach out to us directly using help@cloudbank.org. So with that, let me see, I would like to introduce our first speaker for today. I would like to remind you and encourage you to place questions that you have in the chat, and we'll be collecting those and referring to them during the Q&A session at the end of this talk. So our first speaker is Dr. Sofia Vallecorsa. She is the CERN physicist and the AI and quantum research lead at CERN Open Lab. So Dr. Vallecorsa, please take over now, and off we go.
Thanks. So I'm sharing my screen. You should see my slides now, I guess.
Yes.
Okay, thank you. So I'll start. This presentation is describing you how we're using cloud to train generative models for high energy physics simulation. The idea is really to accelerate the training process for those large models using cloud native technologies and public cloud. So let me give you just a little bit of background, introducing CERN. CERN is today probably the largest lab for experimental facilities for fundamental research in high energy physics, with its big accelerator complex, and in particular the LHC, which is an accelerator ring of 27 kilometers long. So you can see it here at the border between France and Switzerland. You see the Lake Geneva here with the city and the Mont Blanc, the Alps in the back. The facility is huge in terms of hardware, but also in terms of data, with its 4 major experiments: LHCb, Atlas, ALICE, and CMS, which are scattered across along the ring. We produce, well, for now, we already have more than 400 petabytes of data, so an average of more than 70 petabytes per year. And we expect these numbers to increase when, in a few years, the high luminosity LHC runs will start. The second thing I wanted to introduce, just because a few minutes ago you heard about CloudBank, I wanted to give you also an introduction to CloudBank EU. Our project is done in the context of CloudBank EU, which is a proposal that was awarded by the European Commission, and this is a partnership between CERN and UCSD. And the main objectives are really very similar to CloudBank. So we want to provide a structured access to multiple providers in order to determine what is the best model that can help the research community in Europe, addressing all the technical, financial, and data processing challenges that come with it, taking into account the specifics of the European legislations. So CERN as a contract with Strategic Blue as a cloud financial broker, and today we are deploying 18 use cases in different fields: machine learning, HPC, databases, and also quantum computing. So this is the context. What is the motivation? Why have we started this specific project within CloudBank EU? Now, I saw that many of the use cases that have been presented here are about machine learning and deep learning. Also in the field of high energy physics, this is a very hot topic. Machine learning has been used for many, many years for specific workloads, in particular for the last steps in data analysis, when you really want to have the best possible selection between interesting events and not so interesting events. But deep learning is really something that now is being investigated for applications in many different domains in physics. So throughout the whole data processing chain of the experiment. And that is why it has become a very, very important approach to experimental data processing. Now, this means that at the same time, we need to be able to optimize our deep learning models, so find the best approach to solve our problems, but also optimize the computing models for the community, because it is a very, so far, most of our software has had a very, very different behavior. In general, high energy physics workloads are embarrassingly parallel, and this is really not the case anymore for deep learning applications. The access to large-scale resources, which HPC capability, with the possibility of accessing dedicated software, hardware accelerators, for example, can really help us in the optimization of deep learning models through the R&D phase, but also extend their applicability to a much broader spectrum of use cases. So what we are trying to test with this project is really an hybrid approach, and the idea of using public cloud to complement and extend the local infrastructure at CERN. Okay, this is probably something that that it's very in sync with what deep learning workloads requires. They run optimally on cloud. They follow typical burst out patterns, so all of access to large amount of resources for a limited amount of time, and can profit also for solutions that are developed in other fields that are available as services. This used to be in fact, this is a big change, let's say, in our approach through all our history. Let's say the software models we have developed have always been very much customized. This is not so true anymore, thanks to the introduction of deep learning strategies. So our project is really about trying and understand how to build a sustainable, flexible, and efficient burst out approach for CERN local resources to public cloud, and at the same time evaluate how up to which extent we can use already existing services such as ML or DL as a service on cloud. Of course, all of this has to go together with the optimization of our of the use we do of these services, and the possibility to predict and optimize cost. From a technical perspective, this translates into understanding what are the communication costs in our workload. You will see that the specific use case that we chose is very compute bound, so is not much affected by internode communication, but this is not always the case. We need to evaluate what is the physics accuracy that we obtain at using this approach on large models, and also what is the optimal deployment strategy. Now, concerning this, and before really going through the details of the use case, I also wanted to stress again something that probably was already pointed out many times, there are different ways of doing automated deployment on public clouds, and there are different levels of automation, starting from a very low level management of virtual machines, basically no automation at all. So this means that most of all the infrastructure setup is something that needs to be done by the user. From there, we can move on to using open platforms such as Kubernetes, for example, Kubeflow specifically for deep learning workloads. And in this case, we can abstract most of the infrastructure layer, and we as users don't need to worry about that. And this is the approach that we tested on Google Cloud. And the additional level, as I mentioned before, is represented by services. So ML as a service frameworks that are provided by vendors. In this case, we tested Microsoft. We tested it on Microsoft with Azure ML as a service. So, what is our use case? I mentioned generative models, and I mentioned high energy physics simulation. The standard or the classical, conventional, if you want, approach to simulation is the Monte Carlo algorithms. Now, this means that we need to be able to use Monte Carlo to model very complex physics and very complex geometry from the point of view of the detectors. Those are made by millions and millions of channels, and the behavior of each one of each specific channel in the detector needs to be simulated correctly. So this, as you can imagine, is a very expensive task in terms of computing resources, and we evaluated that more than 50% of the all worldwide LHC computing grid, which sums up to something like 1 million cores, spread out hundreds of computing centers. So all of this is used for producing Monte Carlo simulations. In fact, one of the experiments, the Atlas experiment, had measured a number that went up to 70% just a couple of years ago. So this is very, very big numbers. And we expect this compute requirement to increase by a large factor when the high luminosity LHC will start running. Now, all of this has triggered a lot of research in terms of alternatives, fast alternatives to Monte Carlo simulation. The idea is to really trade a little bit of the accuracy you get from Monte Carlo and getting instead a more, let's say, lightweight approach. So generative models, deep generative models are among the preferred, or let's say the most studied architectures today. And in particular, generative adversarial networks work very well in this context because they are able to produce very, I would say, high resolution output, in spite of the fact that their training is particularly difficult and rather unstable. So in this context, of course, it is important to be able to speed up training as much as possible to account for the complexity of the models that is really increasing, but even more, because what we would really like to do is to avoid to prove that this is a model that an approach that can be generalized to different detectors. So this is a very interesting line of research. Of course, fast inference is also important in this use case. As a secondary objective, we could think that improving on the inference of a generative model could indeed allow us to do data, so synthetic data generation on the fly. And this would have an impact on the storage requirements, and therefore, allow us to use most of the storage in our facilities for the experimental data instead of Monte Carlo. Okay, so how would you go about developing a generative model for simulating the output of a detector? You see an example here. The first thing you need to do is basically recasting your physics problem in something that is common to other fields. For example, computer vision, if you want to use convolutional neural network or other. This is the approach that we used. We have represented the volume of a detector as a grid of pixels. In this case, is a three-dimensional grid of pixels. Each one of the pixels represents the output of one of the sensors in the detector. And then what we want to do is to train a GAN, in this case, so a generative adversarial network, to reproduce the correct pattern that a particle generates inside the detector sensors. It's a detail at this level. For this specific use case, we focus on one of the detectors that is most time-consuming in terms of simulation, and so it's basically a very highly granular detector that is used to measure the energy of the particles. As far as generative adversarial networks are concerned, I'm not going to spend time on On the architecture itself, it's one of the most interesting architectures available today. I would say it is built of two networks that are trained once against the other, but really once the training is done, it's only one of the two networks, the generator network, that is used for simulation. So it's the network that has to learn the underlying probability distribution function that describes the best the training data. So the specific prototype we use is based on three-dimensional convolutional layers, and that's why it has, as I mentioned at the beginning, it's a very compute intensive algorithm. It's because of the three-dimensional nature of the operations that we use in our primitives. The detector is represented as an image with these dimensions. What you can see some projections here. You have to imagine your three-dimensional cube and these 2D slides that you can create along the three axes. And a typical particle pattern would look like this in the transverse plane and in the longitudinal plane. So the specific features of this image interpretation, if you want, is the fact that they are very sparse images and the pixel intensities have a very large dynamic range. So this makes the problem hard and very different if you want from typical RGB images that are used analyzed in computer vision problems. So the network is not really big. The overall GAN architecture sums up to something like 2 million parameters. So if you compare to typical convolutional neural network architecture, or now even those models that are developed for natural language processing applications, this is a very small model. But even so, it takes about a week to train on a single NVIDIA V100 card. So what we did was to modify or let's say implement distributed strategy in our models using Tensorflow in order to be able to test training on different hardware, in particular comparing TPUs to GPUs. Okay, so Tensorflow has its own APIs that you can very easily introduce in your code. So this was some very, let's say, simple modification that we had to do. And what we did, what we obtained was the possibility to benchmark our model on TPUs, different versions. We tested version 2, version 3 TPUs that are available on Google Cloud, obtaining, of course, much better results with version 3. This is the time to train for 1 epoch our model. We did some optimizations, for example, trying to see whether optimizing batch size would really give us an advantage in terms of training time, which is the case. And this is tricky because what we need to do is always keep in mind that increasing batch size too much might change our performance in terms of physics, and I will get back to it. But particular for the TPUs, choosing batch sizes that are consistent with the matrix, the hardware matrix that are available in the chip, can really make a difference. In any case, what we obtain, as you see here, is a linear speed up with up to 128 CPU cores. The next step we did was to use a multi-GPU setup. So this was done really scaling, so taking the configuration, the deployment we use locally and scaling out to Google Cloud. And we went up to 128 V100 GPUs in different configurations. The plot you see here, or the histograms you see on the left, just shows how the training time per epoch changes. Increasing the number of GPUs up to here, then you have also we report also for comparison the CPU times. And again, if we measure the speed up, then we can see that this is really linear or very, very close to it. We did a little bit more than just measuring speed up. As I said, it is important to choose the right configurations. There are many different ways you can actually distribute your workload over 128 GPUs. You can choose different nodes configuration, different communication setup. So what we did, for example, was looking at different batch sizes that would give us that actually do make a difference also in the GPU deployment. You can see here that if you reduce batch size for better generalization, then you end up with longer training time as expected, and the other way around, if you increase the batch size and decide to lose a little bit on the performance, on the accuracy. Here we compared different worker configurations runs. So basically the idea in this case is to compare two different worker distribution over the nodes. Okay, so either using a single worker per node or nodes with 4 GPUs. Okay, we also found out that there can be configurations that can induce instability in the training process. We did a similar test with Microsoft Azure. In this case, we relied entirely on Azure ML as a service. As I mentioned before, so it really meant that we completely forgot about defining the underlying infrastructure. All the cluster provisioning was done by Azure ML service. We run also in this case using nodes, including multiple GPUs, 4 GPUs per node in particular. And also in this case, we measured linear speedup. Again, this is relatively simple to see because the model is compute now. What was also interesting is the fact that Azure ML is automatically optimizing all the dataset management in terms of caching, in terms of prefetching, and also the patterns for doing data loading. And we tried to actually switch off those features and try and see whether we could do better by tuning each one of those parameters manually. And well, the result was actually the fact that we couldn't do better. So this for us was a very, very encouraging result. Okay, we could just use and rely entirely on Azure ML optimization. I mentioned briefly about the importance of checking or validating the performance of those kind of models. Now, I don't want to start a very long discussion, but measuring the performance of generative models can be very tricky in the sense that it's very much related to the specific task at hand. It can rely either, if you need to generate a picture, you can ask a human to compare the fake one to the real one and, assess its quality. In the physics case, it's we can rely on a direct comparison to Monte Carlo, likely. So this is what we do is to basically build a set of features that are meaningful from the physics point of view, and then we try to see a correlation among those features, and we try to see how well the GAN reproduces the Monte Carlo results. This is an approach that is also very much related to the specific detector that we want to simulate, but it really allows us to understand what the behavior of the GAN will be once embedded in the larger data processing framework. So you see here two examples. Those two histograms here represent the energy deposition along two different axes of the calorimeter of the detector. You have to imagine the particle that travels to the detector and deposits a little bit of energy in each one of the sensors, and this is the amount that you would measure, okay, when you travel along or when you look at the transverse section with respect to the flight direction. So what you can see is that the GAN results are very close to the Monte Carlo. We do the same test for the output we get out of the 128 TPU cores run. And well, what you see here is for 64 NVIDIA GPUs. We found interesting the fact that the parallelization that happens in the two cases is actually giving us two different results. We investigated quite a lot to try and understand whether this was just a matter of batch size. It was not the case. There is something that is affecting the quality of the GAN image when we run on GPUs. Just for you to have an idea, a difference like this, where the GAN predicts, let's say, a central value for your energy distribution that is shifted, is important. Okay, it's something that can have an effect on physics. A difference like this, where the GAN is basically overestimating the amount of energy that we expect at the border of the detector region, sensitive region, is not so important, especially because this is a log scale, and so this means that these energies are very, very small. Basically, in real life, a detector wouldn't be able to actually measure this. It would be below the resolution threshold. So difference like this is not critical, but still it's interesting to see that it does not appear in the TPU case while it does in the case of the GPUs. So we are still working on this. So before concluding, I just wanted to give, I mentioned cost optimization. So we also try to have an idea of what would be, the most cost-effective solution. Basically, looking at the physics results up until now, let's say that the time. So physics-wise, it looks like TPUs are a better choice because we keep a better. We can. Keep better accuracy. From the point of view of computing time, so the total training time, TPUs and GPUs are more or less equivalent. So if we compare number of TPU cores to number of GPUs, but from the point of view of costs, the picture is very different. What you see here are two, in blue the cost for reserved instances, and in orange the cost for preemptibles. And this is cost per epoch in US dollars, okay? And up to here, all the big bars are related to GPUs, and TPUs start to appear here. So it means, just to give you an idea, so we have, I don't know if you can read the scale, it's 0.5 here, that if you want to use a TPU to train the 3D GAN model for up to convergence, this would cost something like between $20 and $25, which is a very, as I say when I present this, it's about the price of a pizza in Geneva, so it's very good. So let me conclude. There is an increasing number of deep learning models. So ours was just an example, and not even the most complex one, that are now being studied by high energy physics experiments. So this is increasing the computational cost, the computational requirement, but actually it goes beyond increasing computational requirement. What's happening is really changing the fact that we are changing computational requirement. Access to accelerators such as TPUs or GPUs have become essential. So cloud can simplify for us access to this kind of resources, and of course it can also simplify the task of model development, because we observe that we can indeed rely on already existing services. Of course, using these services requires validation, and it requires also actually us, so people, to learn how to best use them, how to best optimize their model in order to make the most cost-effective choice. So with this, I conclude, well, I thank you for your attention, and also, of course, I wanted to mention all other authors of this work. Thanks.
Wow, fantastic! Thank you so much, Sofia. That's a really, really interesting talk. We have a couple of questions that I wanted to share with you to follow up. So one of them is, obviously, this is a kind of one of the recurring themes in cloud computing is what sort of side-by-side comparisons are available. And so it's really great to see this comparison of GCP and Azure. Can you comment on the sort of the convenience to the project that you experienced in relationship to cost? In other words, you went from using a kind of a manual approach with GCP and the TPUs to the Azure ML service, which seemed to sort of automate the process. Can you comment on the difference of that experience between those two?
So well, what I can say is that from the point of view of using a service like Azure ML, this is something that it's really new for us. It's something that we never expected to be able to do. Again, this is some sort of historical perspective, in the sense that we were always used to having very customized, very different use cases without the possibility to really relying on anything that was developed out of our community. So this is a very good news for us. I think in part is related to the fact that, again, deep learning is meant to be that way. That's the way it's being developed. So from the point of view of the user perspective, I think that is certainly the simplest possible choice. Of course, again, it requires care. So, for example, the fact that, no, sorry, I'm going backward. So this is an example of the kind of studies we did, and trying to verify that indeed the tuning, everything that happens behind within, is something that we understand. So that is something that is very, very important. And maybe from that perspective, something like the Kubernetes, this intermediate step where you automatize only the cluster, let's say, management, that makes us feel more safe, or it's easier also to control and to discuss. But I think that many use cases will also sorry, I can't speak today. Will profit very much from automated services.
Cool, that's good perspective. We have some other questions in the chat. I'd like to get as many of these in as we can. So first, what kind of TPUs were used? One of the questions.
So yeah, we compared version 2 to version 3. So okay. Yeah, so those are the ones that we had access to.
Okay, cool. Mike Norman asks, what is the relative wall time / compute cost to obtain Monte Carlo and GAN results of similar quality?
Okay, so this is a very good question. It depends if we're talking about training or inference. Okay, once we have trained our model, we compare running Monte Carlo to comparing running our generator inference. We are talking about speed up that it's orders of magnitude, from factor 1,000 to factor 100,000. Okay, we measured numbers like that. Now there are caveats into this number that need to be taken into account. The fact that in most cases our Monte Carlo code is not GPU friendly, cannot run entirely on GPUs. So of course, so if we compare different hardware, of course, then we need to take care when we judge numbers. So this is one thing. And the second thing, of course, we need to take into account the time it takes to train the model. Okay, so this is also, but it's also important. But at the end of the day, in a production level use case, what you would do is to train the model once and then use it for all your Monte Carlo production campaigns that now take months.
All right, cool. Let's see, another question from Jacob. From a user's perspective, what do you think about computing in the cloud versus on premises? I know cost comparison is difficult to do. So just in terms of
especially as a user perspective, cost comparison is difficult to do because we have access to our on-premise resources, directly. But from the technical point of view, my experience is that because we are talking about deep learning workloads, cloud computing seem to be, it's optimized for that. So there are a lot of services, and there is basically our models, our workloads run almost out of the box on cloud. And this is still not the case in our local facility, mainly because everything else that is not deep learning has a very different pattern and requirements.
Okay, cool. And this question, I'm not sure I understand it, but I'll just repeat. It says, do you have business case use of high energy physics, TPU, GAN, et cetera, in, for example, an oil and gas project?
I don't understand if it's about physics. So if the question, this is a comment, if there are GAN applications run on TPUs in the oil and gas field.
That's what I'm inferring the question is about. Yeah, maybe the person who posed the question can clarify.
Well, I mean,
yes, with your permission, we are trying to build a model, cloud-based model, that basically takes into account all the oil and gas fields, a lot of information about them, and create a digital twin.
Yes.
And in doing so, I wanted to get your guidance as how we could use your good work.
So well, thanks, but there are a lot of compliments in there. So no, in general, GAN, as other generative models, are one of the approaches that can be used to do digital twins. Now, it also, we need to take care, I think, in what we mean in details about digital twins, whether we are talking about something that is a tool or an object that is capable of reproducing the reality, of producing a copy of the reality.
It's actually both. It's actually both. So we're talking physical as well as data.
Yeah, but what you want is also something that you can interact with, right? Then maybe you inject some modification in your data, and this will generate
much more than that. We're trying to create a decision support system and then an expert system.
Yeah.
So this would be great to carry forward in the direct contact. I think this is a potential for an ongoing conversation. Yeah. So with that, we're at our time limit, and I'll thank our guests for some excellent questions. And again, Sofia, thank you so much for this presentation. It's been really excellent. At this point, we're scheduled for a quick break until 9:45, so we can stop recording, and we'll see you back.